Reflection of light. Light is a form of energy. It cannot be seen but enables us to see. Without light, there will be no sight. We are able to see because light from an object can move through space and reach our eyes. The objects we see are divided into two categories: luminous and non-luminous objects. Objects that emit light on their own are called luminous objects, such as the sun, stars, candle, fire, firefly, electric light, etc. Objects that do not emit light on their own are called non-luminous or illuminated objects. They become visible only when they reflect the light falling on them. For example, the moon, metals, wood, etc. During the day, the sun generates sufficient light to illuminate objects on the earth. The blue sky, clouds, trees, houses, cars are all seen because of the sunlight is reflected off from these objects. Without light, such objects would not be seen. At night, such objects appear black. Since the light is emitted by a luminous object, it must be a form of radiant energy. Radiations can be demonstrated by particles and wave behavior of light. There are some theories that highlight both aspects of the light. In the 17th century, two theories of the nature of light were proposed: the wave theory and the corpuscular theory. In 1675, Newton proposed a theory of light known as corpuscular theory of light. This theory treats light as being composed of tiny particles. This theory describes the phenomena of reflection and refraction and some other phenomena like formation of primary and secondary rainbows. Wave theory of light was proposed by Huygens in 1690. This theory describes light as waves that spread out from the source that generates the light. This theory describes the phenomena of reflection and refraction. It also suggests that each color of light has a different wavelength. In 1900, Max Planck, by combining the wave theory and the particle theory, put forward the quantum theory of light and showed that light can sometimes behave like a particle and sometimes like a wave. Now it is well established that light has a dual nature. Light travels in a straight line. The same can be verified with the help of an activity. When a beam of light is allowed to pass through a series of holes punched in 3 cards, it travels from the source through the holes and continues on to the next card only if the holes are aligned in a straight line. This shows that the light travels in a straight line. Unlike other forms of energy, light can travel through vacuum also. That is how sunlight reaches to the earth. Light can travel through liquids and solids. Different materials have different nature with respect to light. materials can be classified into three groups according to the amount of light passing through them. Materials that allow most of the light to transmit through them are called transparent materials. For example, fine glass, water, etc. Materials that allow some light to pass through them are called translucent materials. For example, ground glass, ice, butter paper, etc. They are semi-transparent materials. On the other hand, materials that do not allow light to pass through them are called opaque materials. For example, wood, metals, stones, etc. Let us see an activity. Take a beaker filled with water having dyes in it that can be seen clearly. If we add a small amount of milk in the beaker, the solution becomes translucent and then the dyes appears blurry. But when we add only milk to the beaker, the dyes are not visible. This shows that the solution is now opaque. While discussing various phenomena of light, certain terms are commonly used such as a ray, a beam of light, a point source, etc. A ray is a very narrow beam or a column of light. It is a hypothetical stream of light that has zero width. Hence, it cannot be observed physically. Practically, it is a straight line path along which light travels and represented by a line with an arrow on it. On the other hand, a beam is a set of light rays. It has a finite width that can be observed physically. However, a beam of light is only visible if part of the light is scattered by tiny particles like dust and water droplets. In general, a ray or a beam of light is directional projection of light energy radiating from a light source. A source of light that can be considered to have negligible dimensions is called a point source. It occupies a very small area and having concentrated output. In actual, no light source is infinitely small, but any small or distant light source, such as a distant light bulb, a star, or the sun, can be treated as infinitesimal point source. Most of the real light sources are extended light sources rather than point light sources. Some examples of extended light sources are the entire sky on an overcast day, a large fluorescent tube. When a beam of light encounters the surface of a medium, it is transmitted, absorbed, and reflected from the surface. And if a beam of light that is neither transmitted nor absorbed but bounces back from the surface of the medium, it is called the reflected light, and the phenomena is referred as reflection of light. When a beam of light falls on a regular and smooth surface, the rays of light are reflected parallel to each other. In other words, the reflected light remains concentrated as a bundle of light. This is called a regular reflection. On the other hand, when the rays of light fall on a rough and irregular surface, they are reflected in many directions due to multiple reflections from the irregular surface. This is called an irregular reflection. Most of us have seen photographs of beautiful natural scenes with a still body of water in the foreground. In the photograph, the object and its image can be recognized easily because the still water behaves like a smooth surface and produces a clear image of the object. Light reflects more from a polished surface than from a coarse one. A smooth and well-polished surface that reflects most of the light falling on it is called a mirror, and the mirror that has a plainer reflective surface is called a plane mirror. It makes the image of the object behind the plane in which the mirror lies, and thereby it is called a virtual image. The image formed by a plane mirror is of the same size as the size of the object and the same distance from the mirror as the object. If the object moves, the image also moves from the same distance but in opposite direction. Furthermore, the image formed by a plane mirror is always upright and laterally inverted. That is, the left side and right sides of the object get interchanged. If we see the mirror image of a word, it would be laterally inverted and we may have a problem in reading the image. Here, the mirror acts as the line of symmetry between the image and the object. Due to the lateral inversion, the word ambulance on the concerned vehicles is written in an inverted manner. This is done so that the other vehicles moving in front of the ambulance on the road can quickly see the laterally inverted image of the title in their rearview mirrors and give way to the ambulance. By using two plane mirrors, multiple images can be formed. For example, if two plane mirrors are kept perpendicular to each other and an object is placed between them, then three images are formed in the two mirrors. If the mirrors are placed at an angle of 60 degrees between them, then the number of images formed is 5. Similarly, if the mirrors are kept at an angle of 45 degrees, the images formed are 7. But if the mirrors are kept parallel to each other, then an infinite number of images are formed in the two mirrors. When a light ray approaches a reflecting surface, the ray that strikes the surface is called the incident ray, and the one that bounces back is called the reflected ray. And the point at which incident ray strikes the reflecting surface is called the point of incidence. Angle between the incident ray and the normal is called the angle of incidence, while the angle between the reflected ray and the normal is called the angle of reflection. In case of regular reflection, the light rays obey the following rules. For light rays striking a reflecting surface, the reflected ray and the incident ray make equal angles with the normal on the surface at the point of incidence. The incident ray, reflected ray and the normal at the point of incidence lie on the same plane. When a beam of light falls normally on a plane mirror, it bounces back along the same line after striking the mirror. Similarly, when the beam of light is incident on the mirror obliquely, it bounces in a different direction and the angle of reflection remains equal to the angle of incidence. A white surface reflects more light than a dark surface. Do you know that white light is a combination of 7 colors of light? We see an object white only when it reflects all the 7 colors. It would appear blue when it reflects blue light only and absorbs all the other colors. Similarly, a violet surface appears violet because it reflects violet light only, and a red surface appears red because it reflects red light only. In contrast, dark surfaces absorb more light. That is the reason a black surface appears black, as it absorbs all the colors of light. Mirrors reflect almost all the light falling on them and have a shiny appearance. We can say that mirrors are the best reflectors. The light reflected by the mirrors is capable of forming images that we can see. Though the image formed by a plain mirror is virtual and cannot be obtained on a screen, still the plain mirrors find a wide use in our daily lives. Besides in our dressing tables and bathrooms, plain mirrors are also used in periscopes and kaleidoscopes. A simple periscope consists of 2 plain mirrors set parallel to each other at an angle of 45 degrees with the horizontal. With this arrangement, incident light from an object is reflected through 90 degrees by each mirror. A periscope is mainly used in submerged submarine to look for ships above the surface of the sea. It is also used in operations during a war by army personnel. It can be used to look over the heads of a crowd or over a defensive emplacement. Whereas a kaleidoscope is a combination of more than 2 mirrors containing loose colored objects such as beads, pebbles, and a bit of colored glass. While looking from one end of the kaleidoscope, light entering from the other end creates a colorful pattern. This colorful pattern is due to multiple reflections of the mirrors. Spherical mirror. A mirror has a smooth and well-polished planar reflecting surface, but a smooth and well-polished curved surface that reflects most of the light falling on it is called a spherical mirror or a curved mirror. A spherical mirror has the shape of a piece cut out of a hollow sphere, whose one side is reflecting and the other side is opaque. There are 2 types of spherical mirrors, concave and convex. If the outer surface, that is, the convex surface, is silvered so that the regular reflection takes place only at the inner surface, that is, the concave surface, the spherical mirror becomes a concave mirror. And if the inner surface, that is, the concave surface, is silvered so that regular reflection takes place only on the outer surface, that is, the convex surface, the spherical mirror becomes a convex mirror. Due to the spherical shape, the normal to the surface differs with each point on the spherical mirror, and hence it reflects the light at different angles. In a concave mirror, the reflecting surface bulges away from the light source. It tends to collect the light that falls on it, thereby it is called converging mirror. On the other hand, in a convex mirror, the reflecting surface bulges towards the light source. It tends to deflect the light that falls on it, thereby it is called diverging mirror. Let us have a look at some basic terms related to spherical mirrors. The point in the center of the original sphere of glass from which the mirror was sliced is called the center of curvature. and it is denoted by C. For convex mirror, center of curvature is behind the mirror, and for concave mirror, it is in front of the mirror. And the radius of the hollow sphere of which mirror is a part is called the radius of curvature, which is denoted by R. Whereas the geometric center of the mirror is called the pole or the vertex of the mirror. It is represented by P. The length of the straight line joining the points of extremities of a spherical mirror is called its linear aperture, and the angle subtended by the periphery of the spherical mirror at its center of curvature is called the angular aperture. Normal to the spherical mirror at any point is the line joining that point to the center of the curvature of the mirror, and the line that passes from the pole through the center of curvature is called the principal axis. Every spherical mirror has a focal point that is located along the principal axis. When a parallel beam of light falls on a concave mirror, it is focused at a point called focus or focal point. It is the point where the rays after reflection from the mirror actually meet. Thereby, it is a real point. When this beam of light falls on a convex mirror, it is reflected away in such a way that the light rays appear to diverge from a focal point. In this case, it is an imaginary point because the rays after reflection from the mirror appear to meet at that point, and the distance of focal point from pole is called focal length, which is denoted by F. Let's consider the reflection of a paraxial ray, that is, a ray parallel to the principal axis by a concave mirror of small aperture. Here, AB is the incident ray, P is the pole, C is center of curvature, and F is the focus of the mirror. Reflected ray passes through the principal focus F. Line joining the point B to the center of curvature C is normal to the mirror at point B. It is clear that angle ABC is the angle of incidence and angle FBC is the angle of reflection. Like plane mirror, laws of reflection are valid for spherical mirrors also. Therefore, angle ABC is equal to angle FBC. Furthermore, AB is parallel to CP and BC is a transversal. Thereby, angle FCB is equal to the angle ABC, as they are alternate angles. Hence, triangle BCF is an isosceles triangle and CF is equal to FB. For the paraxial ray, point B is very close to P. Therefore, FB is equal to FP. It shows that focal point F is the midpoint of CP or half of the radius of curvature. In the same way, relation for a convex mirror can be obtained. To construct the ray diagram using a spherical mirror, certain rules are to be followed. An incident ray traveling parallel to the principal axis after reflection passes through the focal point or appears to pass through the focal point. An incident ray passing through the focal point or moving towards the focal point after reflection becomes parallel to the principal axis. An incident ray passing through the center of curvature is reflected back following the same path. Further, an incident ray passing through the pole is reflected at an angle equal to the angle of incidence. For a concave mirror, as long as the object is placed at a distance more than the focal length of the mirror, a real image is obtained in front of the mirror. When the object is placed exactly at the center of curvature, an inverted image of the same size as that of the object is formed at the center of curvature. But when the object is placed exactly at the focal point, no image is formed because the reflected rays become parallel and can never intersect each other. Since a concave mirror reflects light inward to a focal point, hence it can be used to focus light. For example, it is used as a reflector in a street lamp, so that the light from the lamp diverges over a large area. In the same way, it is used as a reflector in headlights of motor vehicles, reflecting telescopes and solar cookers. And if the object is placed at a distance less than the focal length of the concave mirror, a virtual, erect or upright and enlarged image is formed behind the mirror, that is, inside the mirror as shown. Hence, it is also used as a shaving mirror, makeup mirror, and in ophthalmoscopes. Unlike a concave mirror, when the object is placed in front of a convex mirror, a virtual, erect, and reduced image is formed behind the mirror. It always forms a virtual image as its focal point and the center of curvature both are imaginary. It provides a wider field of view, thereby it is commonly used as a driver's mirror in vehicles for a rear view of the traffic. However, in some countries, the rear view mirror is labeled with a safety warning. Objects in the mirror are closer than they appear, because the image formed by a convex mirror has distorting effects on distance perception. Convex mirrors are used on the roads to view traffic around sharp corners. It is also used as a surveillance mirror, that is, to keep vigilance over the activities of people moving around, and can be seen in various buildings such as shopping malls, stores, hotels, and railway platforms. They are usually mounted on a wall or ceiling and useful in the locations having a limited visibility, especially at curves and turns. It can be noticed that the real image is always formed by converging rays, while the virtual image is formed by diverging rays. While dealing with reflection at spherical mirrors, we have to follow a system of signs called the new Cartesian sign conventions. According to this system of sign conventions, all distances are to be measured from the pole of the mirror. The object is always placed to the left of the mirror so that the incident rays always travel from left to right direction. All distances to the left of the mirror are to be considered as negative. All distances to the right side of the mirror are to be considered as positive. All heights above the principal axis are to be taken as positive, while all the heights below the principal axis are to be taken as negative. As a result of these sign conventions, the object distance is always negative because the object is placed to the left of the mirror. The image distance for a real image is negative, as a real image for a spherical mirror is formed at the left side of the mirror. For a virtual image, the image distance is positive as it is formed at the right of the mirror. The height of the object is positive as the object is placed above the principal axis. The height of a real image is negative as the real image is always inverted and formed below the principal axis. The height of a virtual image is positive as the virtual image is always erect and formed above the principal axis. The focal length of a concave mirror is always negative as its focus is marked in front of the reflecting surface, that is, on the left side of the mirror. The focal length of a convex mirror is always positive as its focus is marked behind the reflecting surface, that is, on the right side of the mirror. In a spherical mirror, there is a relationship between the object distance, image distance, and the focal length of the mirror. This relation is called as the mirror formula and expressed as shown. This formula is valid in all situations for all spherical mirrors. There is one more important term generally used to define a spherical mirror, that is, linear magnification of the mirror. It is the ratio of the size of the image formed by the mirror to the size of the object. It is represented by small m. According to the system of new sign conventions, the size of the object, that is, h1 is positive as it is always placed above the principal axis. Size of the image, that is, h2 is negative for real image as it is an inverted image and thereby the linear magnification is also negative. Size of the image, that is h2, is positive for virtual image as it is an erect image and thereby the linear magnification is also positive. Linear magnification is also related to the object distance and the image distance that can be expressed as the negative ratio of the image distance to the object distance from the mirror. It can be concluded that m is greater than 1 when the image is enlarged and less than 1 when the image is diminished. As well as negative value of m indicates that the image is real and inverted, and a positive value indicates that the image is virtual and erect. Let's try some problems. Find out the focal length of a concave mirror if an object placed at 20 centimeters from it forms a real image at 30 centimeters. Here, object distance u is minus 20 centimeters and image distance v is minus 30 centimeters. By using the mirror formula, focal length can be obtained as minus 12 centimeters. Negative sign indicates a concave mirror. Look at another problem. A 2.5 centimeter tall object kept in front of a convex mirror at a distance of 15 centimeters produces a 1 centimeter tall virtual image. Calculate the magnification and the focal length of the mirror. Since h1 is given as 2.5 centimeters, h2 is given as 1 centimeters, hence the magnification m comes out to be 0.4. This ratio is also equal to the negative ratio of image distance and object distance. Knowing the value of object distance, image distance comes out to be 6 centimeters. Now, using the mirror formula, focal length can be obtained as 10 centimeters.